Hi class. So what I want to talk about now is a little bit about fatty acids. So if we take this molecule that's shown here in black, this is kind of a good example of a fatty acid. A fatty acid has two main components. It has a carboxylic acid, so you see that here on the left. So remember, a carboxylic acid is something that has a carbonyl, so a carbon, oxygen double bond, and an alcohol all on the same carbon. So this part over here, let me highlight it in red, is our carboxylic acid. Right? And then over here is your carbon chain. Right? And so fatty acids tend to have these long carbon chains. So the big point about this is it's almost broken up into two parts. So the part over here is going to be our polar side. And remember, this means it tends to like water or things that are polar. And the term we tend to use that for things that like water is we say that they're hydrophilic. All right? So anything that's hydrophilic is going to tend to interact really well with water. Now, if you look back at the other part, this is our long carbon chain. If you remember from our organic portion, things that are just long carbon chains tend to hate water, right? So it's going to tend to be what we'll say is nonpolar. And then the other term we'll use is hydrophobic. And if you think about this, one of the things that we worry about in New England is, when oil spills on the road and you have rain, they don't mix, right? And so you kind of see these oil droplets. Same if you're cooking, you can put a little bit of oil and it won't mix with the water. Same idea, right? If you have these oils, it's going to fight the water. It's not going to like it. So this works really well in the body because now you have two units, right? One that's polar that interacts really well with water, one that's nonpolar. All right, so if we look at this, let's make a couple of them. And so, excuse my handwriting, I'm just going to kind of do this very quickly. If we make some carboxylic acids with long fatty chains, what you see is they tend to stack the same way. And what they're going to try to do is bury these hydrophobic chains. So what you tend to see with these fatty acids is they'll self-assemble, meaning they assemble without us doing anything. They just want to make this conformation. And the reason they want to do that is they're trying to put everything that's the same. So all these polar groups will be on the left together. It doesn't have to be on the left, but for this example, they all line up together, and then all these hydrophobic chains stick together. And so you get these really nice interactions where these can interact with the water. And now if you look at this middle one, this is the perfect example, it's buried in between these other two groups, so it found a really nice nonpolar group. Now, you could say, oh, well, there's water around it. Well, you're rarely just going to have three molecules. You'll have a whole bunch, and so you can start to bury all of these chains. The other thing, and it's a really neat example because it'll lead us later when we talk about cell membranes, is most soaps kind of work in this idea. All right, so let me draw a little droplet of oil. We'll do it here in this weird orange. So we have a group of oil here. All right, and so it's kind of dirt and grime, and we usually take a shower and try to wash all the grime and stuff off. And so the water likes dissolve likes. So water is really good at removing salts and things like that because they're polar, right? The problem is when you have oils that are nonpolar, water doesn't do a great job. So what soap does, and we put soap here in this nice red so it stands out, is it can look like a fatty acid where it has a long carbon chain and then a carboxylic acid on the end. And typically, what we can do to make it even more soluble is make it a salt. Right? And I'll come back to that idea of how we convert those in a minute. And what you can do is encapsulate a bunch of them around it. And we'll just kind of do this over and over. And so what soap does is it essentially wraps around the oil. And now something that was nonpolar now becomes polar because it's encapsulated, right? Essentially the tails will wrap around the oil, right? Because They're both nonpolar, so they like each other, so they group together. But then you have this really nice polar shell, right, that likes water on the outside, and so it allows the water when you're in the shower or taking a bath to just wash off, or the same when you're washing your hands. The outside part is very polar, and so now it can wash away really nicely with the water. And so that's a neat idea how we use the non-polar tails of the fatty acids to grab the oil, and then the polar heads to wash it away. Let me just come back to another point that we had just looked at. What we can do is if you have a carboxylic acid, if you put a little bit of base, what you can do is pull off this hydrogen. Remember, carboxylic acid, so this group here on the end, is really acidic. Remember, it's acidic because we have that resonance. So acidic means we're going to give up that proton. So if we put a little bit of base, we can actually rip off that proton. And so what we'd get is an oxygen with a negative charge, and then everything else keeps the same, and so we'll just make our carbon chain, and it stays exactly the same. Now, the reason that it's important is things that have a charge tend to be much more water soluble. So while this is good at interacting with the water, you've got this long tail that makes it insoluble in water. By putting a negative charge, you increase the water solubility. All right, so once we put a charge, this one is going to be the more water soluble. All right, so let me write that down because that's an important note. Putting this negative charge makes it more water soluble. All right, so this is a really good trick we use, is that if you want carboxylic acids to be more water soluble, we actually just make the anion version, right? And so we can add some base. A lot of times it'll be stuff like sodium hydroxide or, even if physiological. So in our body pH, this proton tends to come off, and we see this as a negative charge. So having it as a negative charge tends to make it more water soluble. All right, I hope this helps.